Most materials are defined by what they are made of. Steel behaves like steel because of its atoms and crystal structure. Glass is transparent because of the way light interacts with its chemistry. Rubber stretches because of its molecular chains. But metamaterials flip that idea around. Their most important properties do not come mainly from the substance itself, but from the way that substance is arranged. The word metamaterial literally points to something beyond ordinary material. These are engineered structures designed so carefully that waves moving through them encounter a kind of artificial environment. To the wave, the material does not simply look like metal, plastic, ceramic, or glass. It behaves like a new medium with properties that nature rarely provides on its own. That is why metamaterials are so fascinating. They suggest that the future of materials may not only depend on discovering new substances, but on designing new patterns inside familiar ones. The central trick behind a metamaterial is scale. Its internal pattern is usually smaller than the wavelength of whatever it is meant to affect. If the goal is to manipulate microwaves, the structures can be millimeters or centimeters in size. If the goal is to influence visible light, the structures must be far smaller, often at the nanoscale, because visible light has much shorter wavelengths. This matters because waves do not respond to tiny details the same way we do. If the pattern is small enough compared with the wavelength, the wave experiences the whole arrangement as if it were one continuous material. Engineers can then tune shape, spacing, orientation, and repetition to create an effective property that the original substances would never have alone. In other words, metamaterials are less like ordinary raw materials and more like machines built into the material itself. To understand why this is powerful, think about how waves normally behave. Light bends when it passes from air into water. Sound echoes when it meets a hard wall. Seismic waves travel through the ground and shake buildings. Radio waves can be blocked, reflected, absorbed, or focused depending on what they meet. Conventional materials influence waves in useful but limited ways. A lens can focus light. Foam can absorb sound. Concrete can resist some vibration. Metamaterials aim to go further by shaping the wave's path more precisely. Their inner geometry can be designed to block a wave, absorb it, guide it around an object, intensify it in a specific region, or bend it in a direction that ordinary materials would not allow. The result is not magic. It is wave physics controlled through architecture at a very small scale. One of the most famous ideas in metamaterial research is negative refraction. In normal refraction, a wave bends in a predictable direction when it enters a new medium. This is why a straw in a glass of water appears shifted. The material has a positive refractive index, so light changes direction according to familiar optical rules. A negative refractive index is far stranger. It means the wave bends to the opposite side of what we expect. Natural materials generally do not show this behavior for ordinary light in a useful way, but engineered metamaterials can be designed to produce it for certain wavelengths. This attracted enormous research attention because negative refraction opens the door to unusual optical devices. It suggests lenses that could focus waves differently, antennas that could direct signals more efficiently, and systems that control electromagnetic energy with a level of precision difficult to achieve using normal materials. The idea of an invisibility cloak came from this same logic, although the real science is more limited than the fantasy version. In principle, if a material can guide electromagnetic waves smoothly around an object and then restore them on the other side, an observer might receive waves as though the object were not there. Early demonstrations used gradient index materials, where the effective optical properties change gradually through the structure. This can steer waves along curved paths instead of letting them scatter normally. But practical invisibility is extremely hard. A cloak might work only for a narrow range of wavelengths, from particular angles, or under controlled laboratory conditions. Still, the achievement was important because it proved a deeper point: materials can be engineered to control the geometry of wave travel. Even partial cloaking shows that wave paths are not fixed by nature alone. They can be designed. Metamaterials are not only about light. Acoustic metamaterials apply similar principles to sound. Instead of arranging structures to interact with electromagnetic waves, engineers design patterns that influence pressure waves traveling through air, water, or solids. These materials could absorb specific frequencies, redirect sound, improve ultrasonic imaging, or create unusual filtering effects. This is useful because sound control is often a trade-off. Thick insulation blocks noise but takes up space. Conventional acoustic panels work well only in certain ranges. A carefully designed acoustic metamaterial can target wave behavior more selectively. In medicine, improved ultrasonic sensors could mean clearer imaging or more precise diagnostics. In industry, acoustic metamaterials could help monitor infrastructure by detecting changes in vibration patterns. The same basic idea remains: do not just choose a material that reacts to sound, design an internal structure that tells sound how to move. Seismic metamaterials push the concept to an even larger and more dramatic scale. Earthquakes send waves through the ground, and those waves transfer destructive energy into buildings, roads, and bridges. The idea behind seismic metamaterials is to shape the ground or foundation environment so that seismic waves are redirected, scattered, weakened, or filtered before they reach vulnerable structures. This could involve arrays of columns, boreholes, barriers, or engineered foundations arranged in patterns that interact with long seismic wavelengths. The challenge is enormous because earthquake waves are powerful, complex, and spread through messy geological environments. Yet the potential is equally significant. Instead of only making buildings stronger after the shaking arrives, engineers could one day design surroundings that reduce how much shaking reaches the building in the first place. It is a shift from resisting waves to managing them. Another major application area is antennas and communications. Modern wireless systems depend on controlling electromagnetic waves at many frequencies, from radar and satellite communication to battlefield networks and high-frequency data links. Metamaterials can help build compact lenses, radomes, filters, and antenna components that shape signals more efficiently. A high-gain antenna, for example, needs to direct energy strongly in a desired direction. Metamaterial structures may help focus or steer that energy while reducing size or improving performance. Radomes, which protect radar and antenna systems, must allow useful signals through while shielding the equipment from weather and damage. Metamaterial designs could make these covers more selective and effective. In aerospace or defense environments, where weight, size, and reliability matter, even small improvements in wave control can become valuable. Here, metamaterials act as precision tools for managing invisible communication pathways. Metamaterials also raise the possibility of superlenses. Ordinary lenses are limited by diffraction, which prevents them from resolving details smaller than roughly half the wavelength of the light being used. This is one reason microscopes have limits. A superlens based on metamaterial principles could, in theory, capture and amplify information that ordinary lenses lose, including near-field details that fade quickly away from an object. If practical versions can be built for useful wavelengths, they could improve imaging in science, medicine, and nanotechnology. But the phrase superlens should not be treated as a finished consumer product. There are difficult problems involving losses, manufacturing precision, bandwidth, and scale. The important point is that metamaterials give researchers new optical design rules. They make it possible to ask whether resolution limits that once seemed fixed can be approached in entirely different ways. The list of possible uses is unusually broad because waves are everywhere. Sports equipment can be designed to manage vibration and impact more intelligently. Optical filters can select wavelengths with greater precision. Medical devices can use engineered wave behavior for sensing or imaging. Smart solar power systems may benefit from structures that trap, guide, or manage light more effectively. Lasers could use metamaterial components to control emission and focusing. Sensors could become more sensitive by enhancing local fields around tiny signals. Infrastructure monitoring could improve if materials detect or guide vibrations in ways that reveal cracks, stress, or hidden damage. Not every proposed use will become practical, and some may remain laboratory demonstrations. But the range of applications shows why the field is so interdisciplinary. Metamaterials are not one product category. They are a design philosophy for controlling waves across many industries. That interdisciplinary nature is one reason metamaterial research moves through so many fields at once. Electrical engineers study how they affect circuits, antennas, and electromagnetic signals. Optical scientists investigate how they bend, focus, or filter light. Materials scientists examine fabrication methods and durability. Nanoscience becomes essential when the structures must be smaller than visible wavelengths. Solid-state physics helps explain how waves interact with periodic structures. Semiconductor engineering matters when metamaterials are integrated into chips or photonic systems. This combination is both a strength and a difficulty. A design that works perfectly in a simulation may be hard to manufacture. A structure that performs well at microwave scale may be extremely difficult to shrink for visible light. A material that shows an amazing effect may lose too much energy to be useful. Progress depends on connecting theory, fabrication, and real-world engineering. One of the more futuristic directions is optical computing. Conventional computers move information mostly through electrons in circuits. Optical computing uses light to process or transmit information, which could offer speed and efficiency advantages for certain tasks. Metamaterial-based systems may be able to manipulate light in compact and highly controlled ways, potentially performing operations that would otherwise require bulkier optical components or more energy-intensive electronic processing. This does not mean metamaterials will simply replace modern chips. Computing is a demanding field, and practical systems must be manufacturable, reliable, programmable, and compatible with existing architectures. But metamaterials could become specialized components that handle particular transformations, filtering tasks, or signal processing steps efficiently. Their value would come from doing physically, through wave behavior, what software or electronic circuits might otherwise have to compute more slowly or with more energy. The deeper lesson of metamaterials is that material properties are not only found. They can be programmed into structure. By arranging ordinary substances in extraordinary patterns, engineers can create effective behaviors that seem unnatural, bending waves backward, guiding energy around obstacles, filtering sound with unusual precision, or protecting structures by shaping vibrations. The field still faces real limits. Many designs work only for specific wavelengths. Some require difficult nanoscale manufacturing. Others lose energy, operate only in narrow conditions, or remain too expensive for broad use. But the conceptual breakthrough is already powerful. Metamaterials give scientists a new way to think about matter, not just as chemistry, but as geometry, pattern, and interaction. If the 20th century was defined by discovering and refining materials, the next stage may be defined by architecting them from the inside out. If you found this helpful, please like this video and subscribe for more explainers.